Hello, everyone. Welcome to another episode of the GDS tutorial series. This is hosted by APS and, as such, is governed by the APS Code of Conduct. Today, we'll be hearing from Stephen Spurgeon from the National Laboratory of the Rockies and Colorado School of Mines, speaking on AI on the atomic edge, how autonomy is reshaping material characterizations and processing. All right, take it away, Stephen.
All right, thanks so much, Adam. Really excited to be here today to share what we're doing in autonomy and specifically focused on the work that we're doing at NLR and Colorado School of Mines in autonomous material science. So I wanted to begin first by talking about the materials data challenge, how we're kind of framing this problem. This is a relatively new area of research, and so understanding the needs from the domain side, the materials side, as well as the data science side are really critical in that. Then I wanted to talk a little bit about machine learning specifically as it applies to materials characterization and processing, what some of the considerations are there. Then I want to talk about kind of AI in action and how we're moving from manual human-in-the-loop workflows to more autonomous discovery workflows. Then I wanted to talk about kind of building scientific instrumentation, specifically electron microscopes that are self-driving, that embed machine reasoning into their control, into their decision making. And then at the end, I have some resources, kind of opportunities from further learning for folks to take away from this tutorial. So at the highest level, we're guided by this materials and kind of device imperative, which is that we want to develop new materials that are better performing. For example, microelectronics, batteries, various modes of energy production and storage. And our goal here is to accelerate the R&D process, discover these materials more quickly, design and deploy them more quickly, and then assure their performance in a given environment. Ultimately, this is, of course, very important to secure and resilient power and energy systems, and of course, from industry perspective, ensuring device reliability out in the field, and especially in extreme environments. And so these are some of the core themes of my research group that we focus on. Now, I wanted to just briefly touch on our laboratory, the National Laboratory of the Rockies, formerly the National Renewable Energy Laboratory. We're one of 17 Department of Energy laboratories, and our mission is very much focused on translational science. And so my group at NLR and Colorado School of Mines is focused on kind of the whole life cycle of functional materials and their scale up and their eventual deployment. And so everything from synthesis to degradation and final breakdown of these functional materials. So our group is really guided by understanding the emergence and the loss of order in materials. And so when we synthesize materials, our goal is typically to harness order at some level and to control and direct order toward achieving a specific functionality, whether that might be electrical properties, optical properties, magnetic properties. And then as we deploy those materials, we put them into extreme environments, for example, of radiation, heat, electrical bias. There's a loss or a change in that order. And so we're trying to understand and derive an order parameter for that entire materials life cycle so we can control materials performance for a given application. At the heart of what we're doing is integrating material science with data science. And our goal is to take these concepts in material science of understanding order and matching them on the data side with the notion of an ontology, which is really kind of a systematic mapping of data to semantic concepts across spatial and chemical and temporal scales. And so on the right here, it's an example of a titanium superalloy that is being investigated kind of from the macro scale all the way down to the atomic scale. And so this is a really nice review by Surya Kaladindi. But basically it illustrates that our goal here is to encompass, 10 to the 8, 10 to the 9 orders of magnitude in spatial scale, incredibly minute details at chemical and temporal scales, and to build an ontology to link information about materials across these length scales. Our goal as material scientists is to manipulate structure and chemistry and composition at every level to achieve functionality. And on the data side, we need a way to describe the hierarchy. So our solution in our group is really to use machine reasoning to go from the atomic level to the device level. We're trying to integrate autonomous characterization with intelligent processing to really derive what we call kind of predictive materials on demand. These are materials that could be designed for specific supply chain constraints, specific performance constraints, and specific form factors, operational envelopes. And to do this process of scale up, to go from atomic level to device level is really, really challenging. And it typically entails looking at vast amounts of data, multimodal data, time varying data. And this is where machine reasoning can really help us in this process. So the data challenge that we face is over the decades, in our field in particular, in characterization and processing of materials, we've gone from completely human-in-the-loop workflows, shown on kind of the left side of this graph, from nearly 100 years ago, where we're manually interrogating and controlling and making every decision along an entire kind of experimental process, to now high-speed detectors, multimodal detectors, decision-making frameworks that are orders of magnitude faster in their data production and hence require new ways of making decisions based off that data. So on the right here, traditional analysis workflows where we're thinking about kind of trial and error experiments based on intuition, collecting, harnessing, analyzing a few of the data streams that are generated, choosing features by eye, and then iteratively developing models based on this, simply not compatible with the volume of data generation, the pace of decision making that's needed today. So our goal in our group is to kind of move to a more augmented and eventually autonomous workflow where we're integrating different types of experiments, collecting and making decisions based on all the data streams available to us, integrating machine learning into this process because it's better at synthesizing multimodal data, reproducibly analyzing large volumes of data, and then using that to ultimately extract models that are more accurate and more representative of a material's life cycle. And so this is something that the whole community has been wrestling with, and I'm going to show a slice of what we've been doing in this area. But the goal here is really to speed up the process of materials discovery and design. So our ontology at the end of the day is based on harnessing different types of data. Our typical problem is an inverse problem, where we are trying to go from some unknown structure back to a prediction of what that structure actually is. And kind of the holy grail of material science is understanding the position of every atom in 3D space, what the identity of that atom is, and then how to manipulate that toward a desired end goal. So in our kind of inverse problem, what we're looking at is trying to solve an unknown structure via sampling some parameter space through a series of experiments. And in electron microscopy in particular, we do imaging, diffraction, in situ, spectroscopic experiments. These all give us different facets of that unknown structure, whether it be information on microstructures, crystallography, materials dynamics, electronic properties, and responses of materials. And we try to assemble this all into, some knowledge of that unknown structure. And over the last decade, we have developed a variety of different machine learning, kind of statistical analysis and computer vision-based approaches to this. These offer an inherent scalability, robustness to noise, greater sensitivity and reproducibility than some more conventional methods. But at the end of the day, our goal is to develop a prediction for that unknown and approximation of that unknown as best as we can, and to do this quickly and across different materials and chemical systems. Okay, so to begin with, I wanted to talk a little bit about, kind of the first topic, which I think is something that as data scientists, it's inherently obvious, but for folks who are on the more of the material science side, it's very important to understand that the models that we're developing, any type of machine learning that we're doing, is predicated on good ground truth data. And so I wanted to begin by just touching a little bit on how we actually collect data, what some of the important considerations are. And this will get a little bit into the weeds of electron microscopy, but it's important for those who aren't familiar with the field to understand what really goes into our experiments and how we can then validate the information that we're training our models with. So in our work, we're very focused on integration of materials. And so integration in terms of functional materials, thin film materials, is central to development of many devices. In particular, we're looking at materials for advanced microelectronics and sensing and memory applications. And the way that these materials are synthesized is really via two different techniques. One is kind of a top-down epitaxial transfer. This is known as kind of remote epitaxy. And the idea here is that we can develop materials that would be very challenging to synthesize together, and instead develop them and synthesize them on different platforms, then exfoliate and transfer those materials and sandwich them and kind of layer them into a final device. And so in this way, we can basically make a whole palette of individual components of materials and then layer them and to create novel devices that would otherwise be very challenging to integrate onto a single substrate. Alternatively, the kind of the conventional approach is what's known as bottom-up epitaxial growth. These are things that the semiconductor industry has used for a very long time. But these are basically physical vapor deposition, chemical vapor deposition type techniques in which we use a single substrate. We control flux of atoms and different alloying elements and deposit them in a controlled manner onto that surface. And then we layer materials. Now, the challenge here is everything is constrained to the same underlying substrate. And so there's a variety of different defects that can form in these systems. Oftentimes, it's very challenging to stabilize many of these heterostructures. Regardless, in both cases here, our goal is to understand these interfaces and what the actual resultant products are of our synthesis. So our knowledge of materials design and development of these sorts of functional systems depends on analyzing them at the most fundamental level, all the way down to the atomic scale. So on the left-hand side here, we've got examples of macro scale images of these materials. And then what we do is we can use a variety of different sample preparation techniques to cross-section and to image these materials. Conventionally now we use techniques like focused ion beam preparation to actually ion mill cross-sections into these materials. And then through careful preparation, careful imaging, we can analyze these materials microstructures down to the atomic level. The techniques that we use have evolved over time. In the past, when I was a graduate student, we did a lot of mechanical preparation, actually pan polishing materials. What you're seeing on the right now is focused ion beam preparation. But the key here is that sample preparation and ensuring the integrity of any data that's generated from our samples is the very first step to getting really good validatable models from our materials. What we've then done is we've investigated the effects of sample preparation on the quality of data. And so the idea here is that depending on how the material is prepared, what condition it's seen before, you can get vastly different quantifications and actually errors in your analysis of materials. And so on the right here, what I'm showing is a sequence of different processing conditions on atomic resolution spectroscopy of an oxide heterostructure. So one of these integrated heterostructures that I showed. The idea here is that depending on the thickness of the sample and resultant beam interactions with the sample volume, you can get delocalization of signals, essentially artificial broadening of interfaces, reduction in signal to noise in your maps that are all just purely artifacts from sample preparation. And so if your goal is to train a machine learning model or any type of statistical model to analyze these interfaces, you need to be able to mitigate and to control for this so that you can ensure reproducibility from experiment to experiment. We also look at other concerns. So when we're imaging things at incredibly high resolution, we're very sensitive to environmental disturbances. So what you're seeing on the left here, kind of linear thermal drift that can occur during imaging, and you see the atoms kind of dancing around and shearing laterally. This can all degrade the resolution of our imaging. And these sorts of artifacts are stochastic. They are, random and depend on the environment from time to time. And so if you're trying to conduct some kind of campaign in reproducible analysis of materials, you need to be able to mitigate against these sorts of artifacts. Again, the goal here is to generate really good validatable ground truth data for a model. So the key here, the key takeaway, just in brief, is that if we want to go from incredibly high resolution imaging to developing physical models for materials and chemical systems, we need to pay a great deal of attention to the inputs into our models. And so this is something that, again, data scientists kind of knows that, garbage in, garbage out. But as a material scientist seeking to employ these models, we need to be really cognizant of the quality of the data that we're producing, the regularity of the data, reproducibility of the data, so that we can consistently use the same parameters in that input data. Okay, so I wanted to now turn my attention to describing machine learning in the context of material science, materials characterization, and processing specifically, because I think over the last decade, as I've worked with teams in this area, we often come at this from two kind of different vocabularies, and it's really important to get on the same page. So to begin with, I think most of us are familiar with what machine learning is, but essentially it's a way to program a machine without explicit instructions. And so in kind of the conventional approach to programming, we have a set of qualifiers that we can test for. And this is a way to discriminate information. And so if, for example, we're trying to identify a cat, we could define very specific factors that constitute a cat, whether it be pointy ears and whiskers, and then a discriminator can learn to basically distinguish one image from another. The downside to this approach is that it's brittle, it's inflexible, and if those rules that we define aren't explicitly met, then we'll fail, even though, an object may be a cat. So in the artificial intelligence and kind of the machine learning guided approach, we're learning from data. We're learning the features and that constitute a cat. And the way we do this is we have labeled ground truth. We provide a model with labeled examples. There's a process of training in which a convolutional neural network or other architecture is learning the relationships between features in the data that constitute these labeled examples of cats. And then what we're providing is a probabilistic estimate, a confidence interval that any given unknown image is a cat. And so the advantage here of this model is that it's more robust and flexible to variability in our imaging. For example, changes in illumination, changes in fur texture, whatever it might be. And these models can scale much more effectively. The downside is they typically require more upfront training and development, and there's a substantial amount of effort that goes into the labeling process. So in machine learning, there's been this progression, and we can kind of match what has happened in machine learning to time frames in kind of material science and material synthesis, characterization, and processing. So in the early 1950s to the 80s, you basically had this rule-based era in which you had symbolic AI, expert systems that were developed. Really at this time, computation was very expensive. And so the primary examples in material science where you're employing data science is in developing design rules, for example, for alloys, to then guess at what the most likely combinations of alloys to give rise to a certain property would be. In the 1990s to the early 2000s, you see the emergence of kind of the classical machine learning era with the support vector machines, decision trees, k-nearest neighbors-based approaches. And here we start to see some of the earliest high-performance computing clusters becoming really abundant in the community. And so here we get things like the materials project where we're trying to predict properties from experimental databases. We start to see the emergence of these very large simulation models. Then in the 2010s, the 2015s, we get the emergence of deep learning, development of ImageNet, using GPUs for specific computations to train machine learning models. And here what we're doing in kind of electron microscopy specifically is looking at crystal structure classifications from diffraction patterns. This is also happening in the X-ray community around the same time. And then from 2016 onward, you see the development of foundation models, transformer models being introduced, more specialized types of computing, unsupervised classification of data from synthesis, characterization, and processing tools, some of the earliest autonomous experimentation in microscopy in particular. And then as we get to the more recent years, we see a lot of an explosion in generative and autonomous approaches, really based around large language models. And the goal being here to use large language models to aid in the process of devising and deploying new experimental workflows. So much of material science, much of characterization and processing has evolved in parallel with these developments in computer science. So then at the highest levels, when we think about the application of machine learning, we can kind of bin them into three areas as it relates to the work I'll show today. One is in this topic of supervised learning, second is unsupervised learning, and the third is reinforcement learning. So in supervised learning, we're acting kind of as a teacher, where we are providing labeled ground truth examples to a model. And these data sets can be things like, for example, known images of particles, known features such as point defects in an image. And the goal is to really predict and classify based on these examples. So one application might be we're analyzing atomic resolution images of a particular microstructure. We know what a point defect or an impurity looks like in that. We can train a classifier through labeled examples of what that defect looks like, provided we have sufficiently robust and representative training data, and that model can pick out those defects at scale. The second approach is an unsupervised learning approach, where we're kind of acting as a detective. And the model here is given unlabeled data and really trying to learn patterns, structures, relationships with minimal to no prior guidance. And so here we can have, for example, unlabeled imaging, spectroscopic, diffraction data sets. And the goal is very much learning relationships and clustering, dimensionality reduction, looking for some inherent structure in the data. And so some examples here, work that's going on is in development of knowledge graphs, feature discovery, from large microscopy data sets or even from scientific literature. And the goal being to really have less labeled data up front, but to learn those associations and then after the fact to go in and potentially label and to derive some physical models from those relationships. The final kind of branch that I'll touch on in the rest of my presentation is reinforcement learning, where an agent acts as a student. And so where this is particularly important is in the development of autonomous systems. And this reinforcement learning process is a model whereby a system can learn kind of the parameter space of decisions and feedback, particularly within an autonomous system. And so we're given an environment, a set of actions, a reward signal. Development of these rewards can be really complex. And the goal is to devise a strategy or a policy that can maximize the reward. And so in autonomous microscopy, for example, it could be taking a survey of a material and then dialing into the points of that material that are most defective or that may contain voids or imaging only the parts that aren't vacuumed, for example, or the surface of a material. And so in autonomous systems in general, in autonomous microscopy, this is a very important way to potentially interact with that system and to program it. So I think the final part of this kind of primer is that as a material scientist working with data scientists, it's very important that we be able to code shift between concepts in material science and data science. And where I see a lot of struggles is we don't always learn the same language, and even the same words can mean something different to each one of us. So for example, in material science, we're often very concerned with quantifying structure, which oftentimes tend to fall into regression type problems. So for example, how can we precisely measure atomic scale strain or polarization in an interface? How does radiation-induced disorder spread from an interface into a material? These are very much regression problems. Second type of problem is identifying features, and these can be kind of classification problems. So how can we determine atomic arrangement where materials meet? How do we map chemical domains that look identical or nearly identical in an image? How do we automatically find and classify nanoparticles by their shape or their morphology? Then the third area is kind of more discovery type problems. And this could be, for example, understanding materials life cycles and degradations. So these are complex. These tend to be kind of multifaceted problems, but how could we, for example, identify atomic pathways for atoms moving through material? How do oxygen atoms move through a complex oxide? How do we discover new phases? And how do we connect initial atomic structure to failure in the real world? So these tend to be much more complex concepts, but the goal here is discovering some kind of underlying pathway, underlying trend in the data. And it is almost a little bit of a synthesis of the two other problems. So the key here is that as we as material scientists interface with data scientists, we need to be able to reframe our problems into a language that is commensurate with the modeling that any data scientist would do so we can select the appropriate tools from our toolkit. Okay. So with that in mind, that little bit of a primer, I want to get into what we have been doing and talk about some specific examples of how we can advance from more manual analysis, particularly in materials characterization and then processing, to autonomous discovery workflows. So most of what we're doing, again, can be framed into terms of either classification or regression. So within classification, we're typically trying to binarize a decision. For example, if we're trying to predict the weather, we want to know, is it going to be cold or hot tomorrow? We're not necessarily concerned with the exact temperature, but within a given range, does it fall into one of these two categories? Second type of problem would be more of a regression-oriented problem where we're trying to predict an exact value. And so it could be what's the temperature specifically going to be tomorrow. And so these are both examples of supervised learning, and they're directly applicable to the types of problems that we're dealing with in material science. So the first example I want to talk about is where we have high knowledge. This is a lot of prior knowledge about a particular experiment. We're going to conduct supervised learning, and our goal here is regression. It's to do fitting of atomic lattices. And so where this is important is that lattices, crystal structures, are so central to every materials device. And our ability to quantify in a rigorous and reproducible way what these lattices are and any distortions in those lattices is absolutely critical for materials development. So in much of my past work, we have been looking at materials like ferroelectrics. And these are materials that exhibit spontaneous polarization that could be switched and is persistent. And so in some of the earliest work that we did here in some of these super lattices, lanthanum chromite and strontium titanate, what we were looking at was high resolution imaging, in which on the left here, you're looking at a high angle annular dark field image. The bright spots in this image correspond to heavier atoms. We're seeing a periodic array of these atoms, so a crystal structure. And this material is a super lattice, so it's a series of layers. Understanding how polarization and atomic displacements vary within the superlattice is critical to controlling any devices based on this. So traditionally, what we would do is we would conduct imaging. We would take great pains to ensure that our drift and other distortions are minimized. And then we literally perform a linear profile of that intensity across the superlattice. The goal here being to quantify the positions of the different sublattices, measure displacements, and then from that calculate polarization. Now, this has worked successfully, but it's a very crude way to do any kind of measurement. And the important thing is that this is a hyperlocal measurement. It doesn't really encompass a lot of the variability that we would see across a broader interface, which we know is absolutely important to understanding device performance. So using kind of the statistical approaches and fitting approaches that I talked about, we can really improve the process of understanding atomic coordinates, measuring these types of distortions. So the way the approach works is that we can use essentially 2D Gaussian fitting to guess at, or rather provide an initial guess for the atomic positions through manual selection or kind of measuring some basis vectors within the crystal. We can then refine atomic position. So the way the process works is we measure distances, we define sublattices through the 2D Gaussian fitting. We then have a map of the coordinates of the atoms within a given sublattice. And then we can calculate in a statistical way what the displacements look like, not just in a single column of atoms, not just in one line profile, but actually on an atom by atom basis. So this is not really sophisticated. It's not necessarily even machine learning. It's just a 2D Gaussian fitting of the atomic positions. But what it allows us to do is to move from raw data to now a distribution of coordinates. And once we have this distribution of coordinates, we can calculate many, many parameters of the material. And in this case, we're particularly interested in displacements between the two different sublattices. The important thing is that we can now apply this process quantitatively across interfaces. We can do it in a reproducible way, and we can do it in a way that is much less prone to human error. So anytime we're drawing any kind of manual analysis, extracting features by hand, there's always opportunity for error. Of course, there's opportunity for error in these models, but the idea here is that this process of fitting allows us to minimize that error, get much more statistics across much larger volumes of materials. So this is another example of where we're analyzing superlattices. And what we're looking at here is, again, breaking down the material into its sublattice components, devising measurements of all the atomic positions, and then measuring these displacements in a quantitative way. So ultimately, what we get out of this sort of very basic statistical analysis is something that goes way beyond what we would do manually. It's much more reproducible and helps us to better understand ferroelectric behavior. So the important point of why I show this is that this is kind of the first starting point for many microscopists who start to employ statistical methods. And there's some downside to this process that we very quickly learn. First thing is that this process of regression is very labor intensive and slow. And so identifying columns, defining sublattices, doing the fitting can be very time consuming, and it doesn't really scale easily without fine tuning to many other types of images or even images of the same material. It's highly sensitive to image quality and noise. And so I already talked about the effect of artifacts in imaging, but many of our experiments are conducted in low signal to noise scenarios, and these models tend to perform very poorly in those scenarios. Third thing is that these models tend to fail in non-periodic or defective regions. And so this is really important that they require a periodicity in the lattice. And if that periodicity doesn't exist for whatever reason, the fitting process can fail. We can get stuck in these kind of local minima that aren't necessarily representative of actual atomic positions. And so as a material scientist, I'm very concerned not just with perfect lattices, but dislocations, grain boundaries, amorphous regions where order is broken, and these models tend to fail in those areas. And really what it requires is good intuition. It requires a high knowledge of the material. You have to make a lot of assumptions about the crystal structure and requires good initial parameters to perform any fitting. And so this is a downside to this sort of approach. Now, machine learning approaches can take us further than this, and they have certain advantages in a few different ways. They offer, improvements upon traditional computer vision that tend to be more robust to noise, and they have greater learning capacity. So this is an example of looking at an interface between strontium titanate and germanium, where the goal is very similar. It's to understand crystal structure of the material. What you're seeing on the bottom, this kind of grid of different approaches, is a variety of adaptive based thresholding approaches, segmentation approaches, clustering approaches, and kind of mapped by their noise sensitivity going left to right, and then their labeling capacity going from top to bottom. So there's a variety of approaches, again, like Gaussian filtering, Otsu's method, adaptive mean thresholding, Gaussian-based thresholding, that are very lightweight and don't require a ton of upfront work necessarily, but they have very little learning capacity, labeling capacity, versus clustering approaches, structural similarity, indexing approaches, even few-shot machine learning approaches require more upfront effort to develop, but they can have a better capacity to describe materials microstructures and better transferability to new scenarios where we have different noise signatures or different artifacts within the data. So the advantage of machine learning is that we can move from these very time-consuming, fine-tuned models that are very brittle to ones that are potentially more transferable. The challenge of machine learning is that we need good training data, as I mentioned. And in microscopy in particular, imaging parameters strongly affect the representation of an object in data. So this is an example of imaging, just shows kind of what scanning transmission electron microscopy imaging looks like. We have a convergent beam that is focused onto the surface, the entrance surface of a sample. The sample is typically less than 100 nanometers thick. The electron beam is scattered through the sample, and then we have a variety of different detectors, both below and above the sample, to generate different types of imaging, spectroscopic and diffraction signals. So what you're seeing on the periphery here, on kind of the left side, the colored images, and then the grayscale images on the right, are all the exact same sample. This is a uranium dioxide material, and what we're seeing on the top left is an X-ray measurement telling us about interband transitions, core shell states in this material. On the left, we're seeing electron energy loss spectroscopy. On the bottom left is a diffraction pattern of the crystal structure. And then on the right, we have bright field, medium angle angular dark field, and high angle angular dark field imaging, which all give us different sensitivities to the microstructure. So the challenge becomes, if you're going to build a machine learning model, which of these modalities do you pick? What imaging settings do you use? What collection settings do you use? Because that can completely change the contrast of an image. You can completely change the signal to noise in your X-ray map, for example. How do you choose some set of combination of parameters to, give you the best, most representative data, and then importantly, build a model that will intake and get that data, same data, every single time so that it can reproduce. That's a major challenge in our field and most fields of material science in general. Unless you're doing simulation, there can be a lot of variability in your input data. So this leads into kind of the second sort of approach that we're taking, which is, again, having high knowledge, high prior knowledge of materials, using supervised learning, but now moving to a more sophisticated classification and segmentation approach. And so here we're going to take the same problem of atomic defect analysis, but we're going to try to address some of the challenges that were laid out in the previous example. So much of the work that we're doing recently has been focused on 2D materials. We're focused on materials like MaxScenes that are one of many classes of 2D materials with promising properties for a range of applications. In particular, MaxScenes are transition metal carbides or nitrides, tend to be one or several layers of these materials that are exfoliated from a bulk crystal. And they have very interesting properties for electrochemistry, for separations, for optical applications, sensing, all kinds of different needs. The goal here is that when we synthesize these materials, there's a wide variety of different defects that can form. They are, again, either monolayer or a few monolayer in thickness. And so being able to quantify these defects at the atomic level in a way that is scalable and that represents the larger volume of MaxScene is absolutely critical. So computational microscopy can play a really important role here. And so what you're seeing on the right is a live imaging of a MaxScene material conducted at 60 kiloelectron volts in our microscope. And the challenge here is signal to noise. We have to be at an incredibly low dose to image these materials. And for a human to interrogate this data is really difficult. So what we typically do when we analyze these materials is we'll take this raw data and perform a registration. We'll take the data, stack it after doing a rigid and or non-rigid registration of the images. We can improve signal to noise, and then we can start to make some sense of what's happening. Now, we've lost obviously time information when we do this. There are some things that are happening in kind of the between frames that we're averaging out here, but this is the only way that a human can interrogate this data. And so what you find in these materials is the lattice of the maxine. You find the brighter spots here in the imaging are actually add atoms on the surface. And then the vacancies here are missing titanium atoms within the maxine lattice. And so through this imaging, we can directly interrogate these materials. But quantifying these defects is incredibly challenging, again, because we have to do so much averaging, or we have to be able to address the ability to look at very noisy, low-dose data in some kind of statistical and scalable way. So the goal here, the question here is how do we go from kind of a very traditional human-in-the-loop workflow to one that employs these approaches of machine learning to get better statistics and ultimately better describe the population of defects in the maxines. So we can use machine learning here and actually use models that were developed originally for graphene and adapt them to the maxine problem. So the way that we approach this is we take a parent image of the maxine that we have collected, that we have calculated ground truth masks for. And the way we calculate the ground truth is through 2D Gaussian fitting. So what we do is we take that initial parent image, we calculate via 2D Gaussian fitting the atomic coordinates, and then we can randomly crop this image and use it as the basis for training a model. So the advantage of the random cropping is that we can take many examples, we can then augment those examples and provide a relatively decent training set for training a convolutional neural network. We can then derive those masks and then provide this as ground truth to train a convolutional neural network to learn to discriminate atomic positions. Now, we're using a model here called AtomAI, developed originally by Maxim Ziadanov at Oak Ridge. And the key here is that we need good input data. We need good ground truth data to train these models. And then there's a wide variety of steps that we have to do in terms of fine-tuning the model. But the point here is that we can take off-the-shelf models and we can adapt them to new scenarios. So what we do is we basically evaluate our performance of our classifier after training relative to the 2D Gaussian fitting. And so what you're seeing here along the top is a training set validation looking at the input image, training mask, the output mask, and then the calculated positions. The bottom here is showing that we can test on unseen data and get really good performance relative to the 2D Gaussian fitting. And the key here is that this model scales. It scales to scenarios of noise, regions that might not be at the exact same orientation or illumination of the sample. And so this is a very powerful approach relative to the more brittle 2D Gaussian fitting. So what this then allows us to do is to start classifying point defects at scale. We can go from these grayscale images to a distribution of atomic coordinates. We can identify where within the lattice that atoms are missing, where the add atoms are, and start to build up this ontology of what defects look like in the maxines in a very statistical way. So where this plays a role then in understanding the synthesis of the maxines is that we can look at the effect of different etching routes on parent maxine and on parent max phases and how that affects the maxine that is formed. We can take a variety of different images of the material that represent all the variability or a good portion of the variability within the maxine. We use these machine learning approaches to classify the atomic and vacancy positions. And then we can take that a step further and actually classify where are the defects within the maxine lattice, how do those distributions change, how do those defects cluster, and come up with an incredibly sophisticated nomenclature to describe point defects within the maxines. This is something that would not be possible with manual analysis. It would not be possible with the 2D Gaussian approach because of the brittleness of the approach. So this allows us then to really describe the defect topology in these materials. We can start to evaluate where defects are isolated, how they cluster together, whether they form complex kind of interlayer structures, even pores in the material. We have error bars and statistics on this. Again, in microscopy, this is something that's often overlooked. We tend to take limited representative examples of the material. But through these machine learning approaches, we can now really build a statistical model of a material. So it's a nice marriage of data science, material science. And ultimately, this is the direction that the field is going to go as we embrace more and more machine learning. Okay, so I wanted to now touch on another example, kind of thinking about, okay, well, both of these examples, the first two examples, had high knowledge, a lot of a priori knowledge of the material. But what if we have low knowledge, less knowledge of the material? Can we still reason in those scenarios? And so I want to specifically touch on few-shot and multimodal learning and how those can help us to understand complex materials microstructures. And the goal here being to understand, as in the case of the Maxine, synthesis products under different conditions. So back in 2019, we thought a lot about this problem because in electron microscopy, we have a massive sparse data problem in the sense that we have very limited labeled examples. Oftentimes our data contain mostly noise or very limited signal. And so the idea that we had is to think about describing materials microstructures in a way that was kind of analogous to what people are seeing when they're interacting with CAPTCHAs. So these are a security device that exists on websites. The idea being that a user is presented with examples that are ground truth, that are known, and then unknown examples, and the user is going to go and discriminate. And so in this case, select every image with crosswalks. In our case, we said, could we use a similar sort of approach to begin training models on the basis of very limited examples for electron microscopy? And so the prompt to a user for electron microscopy might be, look at all the particle data here, select the particles relative to a background. This eventually resulted in a patent that is related to the usage of few-shot machine learning. But what I want to emphasize in this next example is that we have solutions to deal with sparse data. We don't always need massive libraries of large labeled examples to reason in material science. So few-shot machine learning approaches really use limited prior knowledge to classify features and are particularly well suited for discovery, for example, of new materials and chemical systems. So the way the approach works is we take images, we fracture them into chips. These are then encoded using a pre-trained encoder. In this case, we were using a ResNet trained on ImageNet. And then the key step of the few-shot machine learning is that a user at the time of an experiment is providing a limited number of examples. And so in this case, we're looking at an interface between strontium titanate and germanium. The user can go in and select examples of strontium titanate unit cells, of germanium unit cells, and then of this platinum carbon capping layer. So this is a protective layer that we put in during preparation. We then use a type of neural network called a prototypical network to perform comparisons of each of these chips relative to these known examples. The idea then is we can calculate a Euclidean distance in latent space that determines the most likely association between an unknown chip and the user-provided examples. The advantage of this is that we just need a limited number of examples and we start to triage data. We start to make sense of it. This honestly is something that in our field is a very common problem. We have a little bit of user intuition when we approach an experiment. We need to scale and we need to reason based on that intuition. And then as we get new intuition, more information, we can adapt the kind of queries that we're asking. So the idea here is we can go from raw grayscale images, provide a limited number of support set examples, segment those materials, and gain statistics. There's no retraining in the model here. All we're doing is calculating again, a distance in latent space relative to these support set examples and determining the most likely support set association for an unknown. We can then go to other images and just change the composition of the support set. So in this case, we're looking at phase separation and a fuel cell material. And again, select examples of the domains that we care about and then segment those out. And then we can even go to particles. So very different length scale here. We're talking about orders of magnitude in different in length scale. And the goal here being to understand particle morphologies, shapes. Where are the particles relative to a background? And so here we're able to select examples of those different types of particles of the background, and then very quickly triage the data. So the advantage here is one in terms of speed. It is also reasoning on the basis of very limited examples. And so on the left here, I'm showing a movie of literally what we would do in many cases, which is hand counting of features within an image. And so obviously this process doesn't scale. It's prone to error. It's very challenging, obviously very frustrating for a scientist or a student to work on. Using just a handful of examples, typically between 3 to 10 examples of the features of interest, our few-shot model can perform a classification in a matter of seconds relative to the 10 minutes that it would take manually. And importantly, if we have more information, for example, here on the right, our task was find every particle relative to the background. If we want to change that task to separate the particles that are flat versus ones that are on edge, we just change the composition of the support set. And in another 8 seconds, we can discriminate those. So the advantage of the model, again, is that we're able to triage data, reason on the basis of very limited examples. And then if you have more examples, you have more knowledge, more prior knowledge, you can definitely bring that to bear here without concern, and it will even improve the performance of the model. So then the question is, well, what if, image contrast alone is ambiguous? What if it's very difficult to interpret the features that you're seeing? This is where the community as a whole is kind of heading, is thinking about not just one modality of data, but all of the modalities that are available at our disposal. So in kind of the tech community, data science community, there's a lot of talk about large language models that are multimodal in terms of their ability to reason on written text, audio text, uh, images, and designing models that can incorporate all that. We have a very analogous problem, which is reasoning on different types of imaging, diffraction, spectroscopic in situ signals, and using those to perform more advanced reasoning. So these models have exploded. We see a lot of them in terms of different domains of material science, development of autoencoders for predicting materials properties, using them in scanning probe microscopies, even scanning transmission electron microscopies. They're really powerful in their ability to harness different signals of a material and then use that to better describe materials' life cycles. So in our work, we're very interested in understanding materials' life cycles, particularly under extreme conditions. And so traditionally, what's shown on the left here is kind of a manual analysis of a material under radiation. What we're seeing is that microstructure evolving, it's beginning to break up. And on the right side here, we're looking at a Fourier filtering of that to measure crystallinity over time. Now, this really only captures one facet of how the material is responding to radiation. And so we can start to employ multimodal models to better understand not just materials microstructures and crystallinity, but also chemistry and composition. So designing these models requires us to think a little differently than if we're just looking at one modality. But basically, it involves 4 steps. One is that we do pre-processing of our data to ensure that everything is registered, everything can be fit into the same model. We perform a segmentation and classification using an ensemble approach. And then a key step is going from the predictions of our models through a post-classification analysis to something that makes sense to a material scientist and helps us to better understand the physical model for these materials. So the way that we approach it is we basically analyze multiple channels of imaging and spectroscopic data simultaneously. In this case, we're using a few-shot-based approach where we're going to select examples of known regions to classify the unknown regions in this image. But basically, every pixel in our high-angle angular dark field image has a corresponding energy dispersive X-ray spectrum associated with it. We then perform classifications on the basis of just the EDS data, just the HADF or the imaging data, and then we ensemble the two and we average the prediction of the two. And so what we find is that, as you might expect, looking at one modality or another is often outperformed by the ensemble approach, but it really depends on the microstructure. So for example, when we look at this material pre-radiation, the microstructure is relatively simple. It's just kind of a layer here. And so if you looked at classification just based on the imaging or just based on the spectroscopic data, the result is relatively similar. However, when the microstructure is damaged by radiation, when it's more complex, then these models independently tend to perform more poorly than if we ensemble them. And that's because radiation damages not just the crystalline lattice, but it actually can cause migration of different alloying elements, can cause chemical state changes in the material. And that is stuff that is more challenging to capture in the imaging than in the spectroscopic data. When we get to really complex, highly irradiated microstructures, these models perform even better. And in particular, we find that ensemble approaches are really essential to look at highly irradiated, highly disordered materials, where again, disorder manifests not just in a change in the lattice, but also the composition of the material. So once we've got these predictions from our models, we can go back and we can say, well, you've derived these masks, you understand the degree of order in those masks, how can you quantify it in terms of a composition or microstructure? And so we can take those masks and then we can calculate from them compositions within the mask. What distribution of alloying elements are within each of those. And we can do this for arbitrary masks. We can also look at the crystallinity through measuring a Fourier transform of different regions within the material. And what we find, particularly in these systems, is that the initial distribution of alloying elements, having slight defects, for example, in oxygen vacancies, for example, can completely change the response of the material to irradiation in a highly non-uniform way. Okay, so the next example, and then I'll kind of move ahead here, is we are also considering how do we get around with no knowledge, right? So I was talking about high knowledge, low knowledge, now no knowledge. How could we have a model truly discover features within our data? And so I want to talk about the development of graph models and then pull it all together in terms of autonomous platforms that can reason based on those models. So oftentimes we have intuition. We kind of know what's happening. We know the modalities, what we're imaging, and so on. But what if we have little to no knowledge of a material? So for example, here you're looking at different stages of irradiation of a complex oxide, lanthanum ferrite. And our goal here is to see if we could develop a classifier that could, given no prior knowledge, learn features within the data and their association over time. So what we do is we take this image, we fracture it into chips, as we did in our previous approach, and then we project those onto a graph. So the graph here is a way to measure similarity between different regions in the image. Each node on the graph corresponds to a chip, each edge to a similarity index between the nodes. And then we can automatically see the clusters begin to emerge in the image. So again, the model has no prior knowledge of what's in the sample. But what we find is that, at least based off imaging contrast and intensity and so on, there are distinct clusters that form within the graph. We can then take those clusters and back project them onto the image and come up with a classification that would be very similar to what you as a human would do, except the model has no prior knowledge here. So the advantage of these models is they can learn distributions within features automatically. So we can understand how different regions of the material are evolving under radiation, and we can start to back project this onto our material automatically. The important angle to this is that this allows a model to truly discover, to truly learn new features within the data in a way that would be very difficult to do otherwise. If we have very limited prior knowledge or we're looking at a sample for the first time, these sorts of models can help us illuminate regions that might be interesting, that might be outliers within the data, and start to make sense of them. So then, kind of wrapping up what the approaches are that we're taking, we can go from kind of less knowledge to more knowledge. There's different approaches that are suitable depending on what knowledge we have and what specific problem we're trying to tackle. But basically, I think the community has gravitated toward kind of high knowledge models based on simulation, whereas these lower knowledge few shot models and fully unsupervised models show tremendous promise, particularly for materials discovery. And I think we should be paying more attention to those that part of the spectrum as well. Okay, so in the last few minutes of my talk, I wanted to talk a little bit about what these models allow us to do in terms of autonomous experimentation and what some of the important considerations for that are. So one of the key questions we have is, how do we embed machine learning and reasoning into control of our instruments, and in particular, our microscopes? So what you're seeing here is a montage of the commissioning of a JUL grand arm microscope when I was at Pacific Northwest National Lab. Amazing piece of hardware, amazing detectors, but it's still very much human in the loop. We are literally sitting there making every decision for the microscope, where to look, how long to look. And there's a big opportunity for us to reimagine control of our instruments around machine learning. So this is where we get to this kind of scenario 5 of reinforcement learning, where AI models tell the autonomous system where to look. In this case, we're going to talk about a task of kind of sampling synthesis products again. So in this approach, there's kind of 3 steps. One is open loop control, basically pre-programmed control of the instrument. Second is running a classifier in line with an experiment. And the third is performing closed loop control or adaptive sampling of a particular material. So in this approach, it's really important for us to kind of redesign control of our instruments. Control has all been based around the human loop, but over the past few years, we've seen that there's been increasing openness to using application programming interfaces to script instruments. And so on our team, what we developed was a new approach where we took that low-level control of our instrument, everything from the illumination to stage to detectors, abstracted it into a new centralized controller and then we run our machine learning and analytics on top of that. The advantage here is the human is not interacting at the low level anymore. Rather, our AI agents are operating experiments, and the human is interacting with the system at a higher level. So I want to just show like what this looks like, play a very quick clip here, and then I'll tie it all together with the materials example. So what the platform does is it basically abstracts control. We take a readout of all the different components on the instrument. We then can perform what we call open loop experiments, where basically these are pre-programmed studies. In this case, it's a protocol to do automated kind of Google Maps style imaging of the material. And so what you're going to see is the data are coming in at the top here. We're analyzing a microscope sample, taking the data, registering it, stitching it. In line with this, we're able to identify features, for example, landmarks within the data that might merit further examination. We can then have the system move to those coordinates, perform an adaptive sampling, and then in line with this, perform a classification of even finer features. So in this case, we're trying to analyze via that same few-shot model that I showed before, where particles are located. And these particle locations can then drive further decision-making for the autonomous system. So the idea here is that we want to ultimately integrate these types of models with our instrumentation. And the way we're going to get there is to have modular architectures that abstract control, have the human still in the loop, but at a much higher level. And I think this is where the community as a whole is heading. So all of this is built out on APIs that exist. You can go and read about them. But the idea here is that these APIs didn't exist at the time that we were doing this work, and they've since come a long way. And there's opportunity now to start using these tools day to day in all kinds of other experiments. Exist from different vendors as well. So then I just want to conclude here with kind of one final example of the Maxine. So in this case, what you're seeing is automated control of our instruments. We're able to montage materials across vast chemical and spatial scales. And so what we can do is we can integrate this into the pipeline that I showed before. We can collect hundreds, thousands of images of the material and perform classification through machine learning. So the idea here is we take our images of our Maxine that can be acquired using our system. We then classify atomic coordinates, figure out where the defects are, understand the distribution, get that across a vast volume of material at a much greater speed, scale, and reproducibility than ever before. And then what we can do is we can go from that to a three-dimensional reconstruction of point defects in that material, not just in one image, but again, in hundreds of images. And so this is a very powerful approach that demonstrates how machine learning can really take us way beyond what would otherwise be possible if we had the human in the loop in the entire step. So then I think some of the key takeaways are, AI is not a substitute for rigorous science. We need to be aware of what's going into our models, how to collect data the best. Second is we need to frame our scientific question and then match it with a data science question and pick out the models that are most appropriate to our problem. Machine learning can work really well in certain scenarios, but traditional methods can be, simpler to implement, can work for some scenarios, and it really depends on the exact needs of your experiment. Ultimately, we as a community are moving toward multimodal analysis, fusing multiple data streams to get better understanding, and then embedding these into not just analysis, but autonomous experimentation. So with that, I just wanted to thank all of my collaborators at NLR, Pacific Northwest National Lab, and around the country. And I wanted to emphasize that I've got this link here that has a lot more detail on all these methods, and happy to answer any questions and follow-ups here. So thank you. Appreciate it.
Does anyone in the chat have any questions? Feel free to type them into the chat.
So I see one here, this Q&A. I'm sorry. Do you want me to, or are you going to read it, or how do you do it?
Yeah, you go for it.
All right. So Gabriel Mann says, how can one deal with self-healing materials? This is a really good point. So in our averaging our registration, we average in time. And so dynamics are lost at some level. But the advantage here of these models is they can operate in much noisier scenarios than a human would. So we're looking at, for example, watching point defects move dynamically during imaging, tracking those transient intermediate structures that form. I think that's a big advantage of the machine learning models, is that they can just perform better in low signal to noise scenarios.
All right. Well, Thank you very much. Excellent presentation, and we really appreciate it.
Thank you so much. Great to be here.
All right, fantastic. You have a good one.
Take care. Bye.